that's me in a nutshell.
Yes, would mention that Mike Daly in the audience is working out on the project. He's brought in the rain data, and Faye Baird and myself and Lawrence Keenan are all, with Bill Wise. You might remember Bill Wise. Well, anyway, thanks. Sorry to put you on the spot.
Okay.
Well, today's speaker is Stephen Bourne, and also I'd like to introduce Donna Huey, who's also, they're from Atkins. You may not recognize the name Atkins, but you probably remember PBS&J. PBS&J is now Atkins, so we're very happy to welcome them today. Our speaker, Steve Bourne, he says I asked too many questions, so I said, where were you born? He was born in Crewe, is that it? Crewe, England, but he grew up in Bermuda, and so he's sort of taken a general westward path. I checked the map, and he's been moving generally westward. He got his bachelor's degree from Georgia Tech in civil engineering, and he also got his master's degree from Georgia Tech. He is a professional engineer, and you may recognize him. He's done a couple of projects here before when he was with PBS&J, doing Arc Hydro and other water resources, customized GIS programming tools, so you might have seen him here before. Some other projects he's worked on that are interesting that he's not going to talk about today. He's done stormwater systems in Las Vegas, and he did floodplain management in Houston, and also I have to talk about, well, just mention ice road modeling for the ice road truckers in Alaska. He did the really interesting, how much water can you take out of the lakes without damaging the lakes? But today, he's going to talk about, let me just read it, estimating climate change induced shifts in storm intensity and frequency. So, thank you, Steve.
Thanks, Sandra. Yeah, I'm going to be presenting today a little bit of research we've been doing at Atkins into how to estimate how the storm, the character of storms is going to change due to climate change. So I'll just get into this. My name's Stephen Bourne. I'm from Atkins. I work there as a software developer and project manager. The other authors of this paper are Kelly Brumbelow from Texas A&M University, Leslie Gowdish, who's also at Atkins in my group, and Tom Singleton, who's also at Atkins. Let me just go ahead. This is kind of how this research question came up. The current approach assumes stationarity. Raise of hands, everyone who knows what stationarity is. Okay, one person. Stationarity basically means with time series that the mean of the time series, the standard deviation of the time series, the other what are called statistical moments don't change over time. So in other words, your 100-year storm now is going to be the same as your 100-year storm 50 years from now. The assumption is that it doesn't change. Here you can see this is a map from the technical paper 40 from the U.S. Department of Agriculture. And this is what engineers use when they want to design a bridge or something to understand, what is the biggest storm that we can expect? What's our design storm that we have to design the bridge for? You can see down the bottom there at Tampa, the rainfall for the 100-year, 24-hour rainfall storm is 12 inches. That means if you got a storm that lasted for 24 hours, the 1% chance storm that occurs is going to drop about 12 inches of rainfall on Tampa. So this map, essentially, you see there's no change in the map over time. It's assumed to be stationary. And so that 12 inches will be 12 inches now. It was 12 inches 50 years ago, and it's assumed it'll be 12 inches 50 years from now. So our question was, is that really true? Is stationarity a good assumption? This chart right here, this map is from the U.S. Global Change Research Program. That's a NOAA program that's looking into the impacts of climate change. And this is actually from 1958 to 2008. They did an analysis, and what they found was that in general, over the entire nation, we were expecting an increase, or we saw an increase of 5% in average annual rainfall. But if you actually go and look at it on a place-by-place basis, you can see that some places got wetter and some places got drier. particularly down there in the west, the southwest. You can see it's quite significant how dry it got. Whereas up in the northeast, we're looking at 25% increases in average annual rainfall. So this pretty conclusively shows us that the stationarity assumption isn't valid. And so the question becomes, what do we do about it? Here's another chart. This is looking into heavy rainfall across the country. And what it's saying here is that they looked at the top 1% of daily events that occurred in each place and came up with an estimate of how they're changing over time. This again is from 1958 to 2007. And what it's saying here is that up in the northeast, 67% increases in the large storms that occur. So the storms are getting bigger. And interestingly enough, across the entire country, the storms are getting bigger everywhere. Here in the southeast, it's about 20%. And so what does that mean? How do we actually reconcile these two things? One is saying, like in the southeast, if you look there, it's saying it's getting drier on an average annual basis, but the storms are getting bigger, the large storms that occur. So what we can conclude from that is that droughts are going to be longer, or they're getting longer, and when the storms do occur, they're getting bigger. And so that's something that we have to work with when building engineering structures. What will happen in the future? We looked into that too. This is from a suite of global or general circulation models. This is results from those. And they are basically saying that here we have the 4 seasons, winter, spring, summer, fall, and essentially blue areas means it's getting wetter in the future, brown areas means it's getting drier. And so in general, the models agree that the northern part of our continent is going to get wetter, the southern part is going to get drier as we move into the future. This is comparing essentially the about 2100, the year 2100 to now, and that's the estimate. So in Florida, there is, generally our rainfall comes through several different mechanisms. Frontal activity, convective storms, like the one we're probably going to see today, and tropical storms. This map we're looking at right here, I really like it because it actually shows 2 of the mechanisms happening at the same time. This was taken last November. There was a storm that occurred, and we can see actually there's frontal activity. I'm going to try to do this. Never done this before. That is a front right there, bringing rainfall, and this right here is a tropical depression. And so they're both happening at the same time. And the idea is, okay, how are these things going to change in the future? And given that, plus combining that with the idea that urbanization is occurring, the hydrographs down the bottom, they show the result. Essentially, the blue hydrograph is now, and we can expect that as urbanization occurs and connected impervious areas increase, plus intensifying rainfall and larger storms, that you're going to get hydrographs that are, they peak faster, and the amount of rainfall that's coming through the watershed is higher in that flashy event. So how do we study this, and what's the larger framework? To understand what we're actually after here is climate change's impact on things like estuaries, on cities, on watersheds. And so within Atkins, we've set up a R&D program, which is unusual. Most engineering consulting firms don't have R&D programs, but we have that going now. And this is one of the projects that we have going at the moment. This is called the Watershed Health Manager Project, and this chain of models that I have up here, it basically takes the GCM data that I talked about earlier, and then creates a forecast for storms based on that data. It also does forecasting of the urbanization within watersheds, and then brings it all together into an estuary model so that you can get impacts on estuarine environments and habitat based on those 2 factors that are occurring simultaneously in the future. I'm going to be talking today about the StormCaster part of this, but basically this is the larger analysis framework that we're building right Okay, so let's start off with some requirements here for this storm forecast. We want it to go from 2010 to 2100. We want it to be short time steps. In order to understand the impact of individual storms, we have to get a forecast that's 15-minute, 60-minute time steps. We can't really have monthly data. We have to go to much higher frequency than that. We want to capture uncertainty in the forecast. These are forecasts, and the various models we're basing them on, they all disagree to some level. So we have to understand, what is the uncertainty? What does that imply about the forecast that we're getting, and how do we deal with that from an engineering standpoint? And then we wanted it to be applicable in many geographies. So in other words, we want this tool that we're developing to be, we can use it here in Florida, we can use it up in Seattle, we can use it anywhere we want. It's still applicable, and the results are still reliable. So I'm presenting these as requirements, and then I'll present how we actually met these requirements with our methodology. This is the algorithm we came up with. It's a two-step process, and I'll go through it step by step. The first step is preparation. In order to create a forecast, we need some sort of projection of the future, and the state of the art right now is to use general circulation models. And so that's this data set right here. Then another thing we need, because general circulation models are generally known to produce biases in local projections of weather, we need to bring in historical data to get rid of those biases, and that's what this is. So we have an individual site somewhere in the place of interest where rainfall has been recorded for maybe the last 30, 50, 100 years, and we have the GCM providing a projection of the next 100 years. We then have to do some analysis with that in order to prepare to do to build the forecast. And so in the case of GCMs, we have to do something called downscaling, and I'll get into what that is. But the end result of it is down here, which is the downscaled monthly projections. And so you have a set of projections of rainfall for the particular area that you're interested in that the bias has been removed from those. Now that is still monthly though, and so we have to actually convert that to this high frequency forecast that we wanted. And to do that, we have to look at the historic data, and I'll get into how these how the analysis results for this are used later. But basically what we're trying to do with the historic data is to come up with the probability of rainfall on any given day. And so that's what this segment is right here. Estimate Markov probabilities. W-W means wet given wet. So what is the probability that it rains today given it rained yesterday? And W-D means wet given dry. What is the probability it rains today given it didn't rain yesterday? We have to get that information. We also have to build a library of storms from the data. So in other words, we take this 15-minute data, historic data that we get, and we pull out the individual storms. So we look at, we're looking for maybe 5, 10 time steps where there's non-zero rain, where rain actually occurred, and we'll pull that out and say that's an individual storm from an individual month. The idea is that when we get into building the forecast, we're going to use those storms to synthesize a new forecast in the future. So anyway, that gets us all our data that we need in the preparation step. The next step is to synthesize our forecast. And we go in a loop. It's a monthly loop. That's this outer loop right here. And we go through every month from 2010 to 2100. In the event that we see within that month, remember we have this forecast from the GCMs. In the event that that month says, okay, the rainfall in that month is going to be higher than it's ever been recorded before, which is a high possibility given the increasing rain, increasing the trends basically in the rainfall over the next century. In that event, we inflate the probability that it's going to rain. Remember, we got these probabilities over here. We can inflate those, basically scale them up so it says it's going to rain more often. Once we do that, we can then loop through the every day in the month, and we first ask the question, is it raining? If it is, then we select a storm from the library of storms that's been created, and we add that to the forecast. We then loop around to the next day in the month, and the next day in the month, and the next day in the month, adding in storms according to the probabilities that we found. That loop goes through the entire century, and at the end we have a highly detailed, high-frequency 15-minute forecast of storms over the century. I know that was a lot of explanation, but you'll see it in the next charts how that all comes together. First, I wanted to talk about general circulation models. Again, these are the state of the art. This is what you use in order to generate these kind of forecasts. These models are created by centers around the world. There's about 20 of them. And they, each model will cover the globe in pretty large grid cells. They're typically about 2 degrees latitude by 2 degrees longitude. They run them for centuries, so they'll be running these things from 1600 all the way to 2200 on an hourly time step. And the models are coupled models of global, atmospheric, oceanic, and terrestrial systems. So it's a very complex model with lots of hundreds of variables at each grid cell. They are created, basically the body that governs creating these models is the UN IPCC. You might have heard of them before. They specify greenhouse gas emissions scenarios. So they'll say, and we'll get into that a little bit more, but they'll say that essentially the governments of the world are going to govern their greenhouse gas emissions in the following way. They create multiple scenarios and then run those through these models. And the output is temperature, precipitation, lots of different variables actually that result from governing greenhouse gases in the way the scenario says. Here's an example of how big the GCM grid cells are. This is, I was looking at St. Augustine here, and you can see there's 3 overlapping rectangles here. Those are each one cell from one model. And so you can see the cells are pretty big. I mean, they're covering like half of Florida in some cases. The ECM model is the model from Germany, a center in Germany that creates one of these GCMs. The GFDL model is from Princeton, and the MyROC model is from France. So getting a little bit more into the greenhouse gas scenarios, this figure right here is published in the UN IPCC report, the standard report. And it says that, basically they're picking out scenarios such that, the spectrum that they're on are, a world that's more economic or more environmental. That's the up and down axis here. And the horizontal axis is a world that's more global or more regional. And so the scenarios are set such that, they can basically hypothesize the world will be more global and more economic. That's A1, or more regional and more environmental. That's B2, or anywhere in between. So there's multiple scenarios that are set up in order to basically forecast how world governments are going to behave. Using GCMs, what you end up with is each of these models, there's variability in them, both in the model methods, like the actual results that are being produced by the models for the same scenario are different, and also the scenarios are different. And so there's a lot of variability in what's coming out of these models, and generally the practice is to use an ensemble of the models, basically use all of their results as your forecast. And that way you capture all of the uncertainty that's in the modeling process. Now, I talked a little bit about downscaling. Again, this is to remove bias that's coming out of these models. We've found in many cases that, looking at the precipitation that occurs in the model compared to the precipitation that actually occurs in the location of interest, there's a lot of bias there, and you have to get rid of that bias, or your forecasts don't make any sense. And so this set of time series here essentially describes or simplifies what localizing or downscaling is in our case. You start off with the GCM projection here. You'll then subtract it from what's called a pre-industrial control. Pre-industrial control is like a run of the model that assumes that the industrial revolution didn't actually happen. And so it's kind of our control run. because the Industrial Revolution is what is creating a lot of the greenhouse gas effects. So you subtract those two from each other and you get something called deltas. So you can see there that the green line is moving around 0, so it's just giving the departure from 0 relative to pre-industrial control. You then add that to local climate. So in other words, you go get a rain gauge, get the climatology from the rain gauge. That's the average rainfall in January, average rainfall in February, average rainfall in March, and so on. And you repeat that over and over again for your forecast horizon, your 100 years. And then you add that to the deltas, and what you end up with in the end is a localized version of what the GCM projection is. So that's kind of our starting point. That's what we have to do as a process just to get to the point where we have some sort of projection from the GCMs. This is what the end result looks like. You can see there's actually 12 different lines there, and each line represents a GCM and a scenario. And so we have 4 GCMs here and 3 scenarios, so therefore 12 different projections. And so what they come out is what we call an ensemble. This is the monthly projection, therefore, from the GCMs for Tampa, Florida. And we can see, in general, there's a lot of variability here. If you look at this, that's quite significant. That's about 2.5 inches of variability on a monthly basis, which means that the GCMs, they're not agreeing with each other here, and so this is the uncertainty that we have to deal with in the forecast. You can see also that as you get further and further into the future, that uncertainty widens, and so the GCMs are agreeing with each other less and less. One interesting note from this chart, though, is that in general, this line right here, which is the median of all 12 lines, it's about flat. So it's saying that in the future, the GCMs at least are saying that in the future, Tampa is going to have about the same rainfall, even as we move through the next 100 years. So that's an interesting result. More analysis of those 12 lines. Here is, we took one of those lines, basically, and we're trying to compare the historic rainfall climate and the future rainfall climate. And so the bars here, the blue bars, represent the historic monthly average rainfall. The red bars represent the forecast or projected monthly average rainfall. And you can see they're about the same. And so that kind of agrees with our idea that Tampa rainfall really isn't going to change that much in terms of volume. What's really interesting, though, is if you look at the standard deviation of those totals, they stay about the same through the winter months, right? These lines right here, the green line is the historic climatology, the purple line is the GCM climatology, the standard deviation. So they stay about the same in the winter months, so that makes sense. But there's a big gap right here in the summer. And what that big gap means is that historically, we've seen larger storms than the GCM is projecting, much larger storms. If that standard deviation is high, then you have some small storms, you have some big storms, and they're contributing to make that standard deviation. A low standard deviation during the month in GCM data, what that means is that the storms they're much smaller on average, and so the standard deviation is lower. And so that's a result we don't really expect. If you remember the chart that said, what's happening with heavy rainfall, it said it was increasing in the future or over the last 50 years. We kind of expect that standard deviation will get bigger in the future, and so that's something we're investigating right now. We looked at all the models to see if that was true of every single GCM and scenario, and so each bar here basically represents one of the GCMs running one of the scenarios, and if the bar is negative, and you can see they all are, that means that all of them are showing that behavior of smaller storms in the summertime. Now, I mentioned earlier that we were talking about scaling the storms. We're building this forecast from historical storms. And if you get to a point in the future where you see rainfall that's higher than has ever been recorded before, then you have to make the storms within that month occur more frequently and be bigger in order to account for that. And so this chart is about how we came up with how to do the scaling. The left chart here is total monthly rainfall versus mean storm depth for the month of April. And so we can see here that over the historic time frame, in general there's a linear pattern. So if there's more rainfall, the storms get bigger and bigger on average over the month. And so that's this pattern right here, and that verifies our assumption that we can just make the storm bigger if the monthly rainfall is bigger than it's ever been seen before. In terms of their frequency, the chart on the left, what we did was we figured out the dry spell, the mean dry spell in each month in April, and that means just the number of days between rainfall and rainfall, and then compare that to the total monthly precipitation. And in general, we get this kind of behavior right here, which is kind of what we would expect. It says as the rainfall gets lower, the mean dry spell increases more and more. And so based on those two relationships, we can scale our storms as we're building the forecast. So just to go back to this, remember I'm going to show you the result of this now, and I just wanted to remind everybody what this thing is doing. It's going through each month in the forecast. It's determining, it's inflating the probabilities of rain if more rain is expected than has ever been seen, and it's going through every month, every day and every month, and determining if it rains, and if it does, it's sticking a storm in from the historical library. And so this is what it ends up looking like. The orange here, the orange dots are historic storms. So that's from the rainfall site that we've been working with. The blue dots are that's our forecast. And so, running this process, you can see it's high frequency. It's, every 15 minutes we have a measurement for rainfall. And we can see that because Tampa showed that basically the 100-year storm isn't going to change over the next 100 years. This is the estimate of the 100-year storm from the blue dots, and you can see it's fairly flat all the way across. This is the 10-year storm right here. Okay, so currently in our R&D program, we're actually developing a web tool that does this. So you'll be able to go anywhere in the world, basically, and pick a point and say, I'd like to get a forecast for that point. And it's going to go through all of that analysis and produce that chart for you in the end, which you can download and use as use in engineering analysis or research. We of course intend to use it in our larger framework for estimating watershed and estuarine impact from climate change. And this will be open to the public, so anyone will be able to go to this and get their forecast. Future work, we're going to continue developing the tool that I just mentioned and launch it. The summertime reduction in variability that I talked about, that's kind of puzzling, and we want to look into that more. Probably what we'll do is we'll bring in the kind of models that insurance and reinsurance companies use, because they do the extremes pretty well, hurricane extremes. So we want to get that information, and we'll include it as another model within our forecast. And then, we'll continue the larger development of our watershed and estuary assessment framework. And I'll finish up with my favorite forecasting quote. It's very true. So, any questions? Yes, sir.
What is the essential logic connecting increase of global temperatures to increase in frequency or intensity of storms? How does that work?
So, thank you. The question was, what is the central logic behind increasing global temperature and increasing intensity in storms? Correct? I got that right? Okay. I think it's definitely not as simple as people think it is. It's sort of the idea of, increasing temperature is a hallmark of increased energy in the global system, oceans, atmosphere, on land. And the idea is that increase in energy gives rise to basically going to the extremes in terms of, storms that occur, droughts that occur. It's basically pushing the events that occur to be more extreme in both directions. So that's the idea. It's an increase in energy. Does that answer your question?
It's going in the right direction.
Okay.
Yeah,
Yes,
I think
ma'am.
kind of a follow-on to that is you commented earlier that you looked at a period of record from 1958 to 2008, and I understood that you made the projections forward based on the pattern that you saw during that time period.
Right.
Would it be useful to use a longer time period, or is that data available? Or?
Absolutely, it is. The question is, would it be better if we used a longer historical time frame in order to be the basis for our forecasts? And the longer it gets, the better it gets is really the answer. In some places, I mean, if you remember this image right here, you can see the red dots all over the U.S. Those are individual sites that have been recording rain, some for the last 120 years, some for the last 5 years, and it varies a lot. So really, the answer to that is, our tool will use the 120 years if it's available, and we'll cut it off at a certain point. 5 years of data is just not enough to do it. You need to have about 30 years of data to even start to get reasonable answers. And so we'll use as long a time frame as we can get. Yes, ma'am.
I'm curious, you used Tampa as an example, and basically the model indicated that there wouldn't be a great deal of change in precipitation at the time. Have you tried the model in other areas of the United States? Because it's my understanding that the impacts will actually be magnified as you move further north. Have you tried it in other areas of the United States, and are you seeing any trends like that via the model?
We are gearing up to do that, to actually apply this method in other parts of the United States. We're producing this tool that does that whole process more or less automatically. And so once we do that, we'll do an assessment of the United States. But in general, the GCMs do indicate that as you go further north, the percentage increase in rainfall over this century gets higher and higher. And I think it maxes out at about 30%, something like that. Down in Florida, it's kind of in this weird zone where it's sort of neutral. But if you go down into Mexico, you see negative 30%, that kind of thing. So yeah, it's been shown that those trends do exist.
Does the model differentiate between tropical storms, which those would seem to kind of meet your hypothesis regarding total energy available to create storm systems? And does it also look at the mechanisms of the frontal systems, where it seems to me that's more of a contrast in air temperatures that kind of generates the big storms from those, which are two different patterns. It seems like in the second type, contrast in air temperatures, even with the total temperatures going up, maybe there's less contrast.
Right. Sure. So the question this time is you have long questions, Palmer. The question is the model considering the different mechanisms of precipitation explicitly as it creates the forecast? Is it considering tropical storms versus convective versus frontal? Do I have? Okay. It is insofar as it's building that historical library of storms. So it's actually using storms that occurred in July in Tampa, or it's using storms that occurred, so a tropical storm might be in there, or it might not. It's using the mix of storms that occur, and it's building the forecast from those storms. Sometimes it's scaling them, sometimes not. Right. We thought that would be better. It's more believable essentially by using the historic analogs than by generating our own storms using like a statistical weather generator or something like that. We thought it'd be better to just use the historic storms that occurred. We may have to scale them if there's a trend, but essentially they're the same kind of storms occurring in the same kind of way. Ed?
You mentioned your model's using like 15-minute rainfall data.
Right.
So you're using data back in like 40s and 60s, and did you like extract? Did you have 15-minute?
We did. Yeah, we did.
And then you may turn that into a daily forecast.
Yeah, okay. Sorry. Okay, so the question is, we're using 15 minutes historical data, and did that data exist back that far in the past, and are we then converting into a daily forecast in the end? No, we're not converting into a daily forecast. It's still a 15-minute forecast right to the end, because that's what the engineers need, is like that kind of frequency. And only in certain spots in the United States they did actually measure rainfall that far back, and so that's what we're using. I think the Tampa one had 1910 is when it starts. Yeah, and it's 15-minute rainfall the whole way through. Yes, sir.
Yes, if you're using a library of historic storms, if you're trying to predict for a world that's warmer, how does that work? I mean, if you've got more energy that theoretically would produce bigger storms, they wouldn't be in your library.
Right. So, okay. So the question is, how do we know that the storms from history are equivalent to the storms that will happen in the future? And how can we verify that? And that's what this chart was about. See, what we did was we plotted historic total rainfall for the month versus the mean storm depth during that month. And so, the hope was, if there's a relationship like this, we can say, if you get a precipitation that's up here, so in other words, you're getting more precipitation that's ever happened before, that you can extend this chart out to here and say, this is the mean storm depth that we can expect at that point. Once we know that, we can then take the storm that we have, this historic storm, and then multiply it by a factor, scale it up, so that it becomes bigger than any storm that's ever been seen before, even at those 15-minute time steps. And so that's the idea, is we're using this linear assumption here in order to build larger storms than have been seen before.
Yeah, so you basically using the GCM forecast monthly rainfall imposed on historical rainfall, right? So basically, my understanding, you're going to change the intensity of rainfall, but it's not going to change the rainfall return interval or frequency. Is that my understanding correct?
So the question is, are we just changing the intensity of the rainfall and leaving the frequency alone? And again, that's actually the right side of this chart right here. What we've looked at here is the mean dry spell, right? So that's the time within the month, the longest dry spell that occurs within the month. So, one day of rain occurred, and then no rain, and then another day. We're measuring that as a duration. And what we've plotted here is total monthly precipitation again versus mean dry spell in days. And so what we found was that this relationship exists there. This relationship essentially says that, as the rainfall increases, the mean dry spell shrinks. In other words, there's more and more days where it's raining, and you can't find a long dry spell within a month like that. Or within a month with large total mean precipitation. So we, again, just like we inflate or we extrapolate this relationship right here for the size of the storms, we also extrapolate in terms of how often they occur. We get from the historic data these Markov probabilities, which is, probability it's going to rain one day given it rained yesterday, probability it's going to rain one day given it didn't rain yesterday. And those are going to end up being, 60%, 30%, those percentages basically. We inflate those percentages based on this relationship on the right. And so what that does is make the storms happen more frequently, and that changes the return period. So we're doing both of those.
I think you add the delta, you add the GCM forecast minus the industrial trend.
Right.
The delta you add onto the historic rainfall. Is that
That's a different process. That is the downscaling, but that's still at monthly time step. So that's just getting the GCM monthly projection. The process for creating the forecast comes after that. Once you have the monthly projection, that just gives you, basically that gives you the dots that are on these two charts right here. That's the monthly data. We then have the process of converting that into 15-minute data, and that's where this relationship comes in. Yes, sir.
Are these magnitude frequency relationships developed regionally? Or is this still a global picture?
This is local. This is for specifically for Tampa. Yeah.
Okay, so it would be different.
Yes, it would. I'm sorry. I was reminded to repeat the question. The question was, are these relationships that we're looking at in these charts global, or are they developed locally? And they're developed for each individual location of interest.
Have you had the opportunity to plot like the predicted values against what's actually occurring today, per se? Like the proof in the pudding?
Right. Also known as validation. Yeah, we haven't gotten there yet. No.
Is that part of your QA/QC prior to implementation on a larger scale?
Yes, we're looking into that. I think we have like bigger fish to fry here, particularly in terms of that summer difference in standard deviation. I mean, the GCMs are all saying that the storms within the summer are smaller than we've seen historically, whereas you're getting a lot of predictions out there that hurricanes are going to get bigger and bigger, so that doesn't really go together. And so we have to figure out how to fix that. Or otherwise, if we do validation right now, we're going to find that summertime we're not doing very well at all. So that's kind of our next step.
So what you're saying there then is if your mean rainfall increases, the storms get bigger and the frequency gets higher as well. So you're not accounting for then, or are you, one super hurricane that comes in, and you see what I'm saying? If you have one large tropical system, that can really kind of skew things.
Yeah, and that's sorry.
That should be running around with the microphone.
The question was, are we accounting for the very large storms that occur within this process? A large hurricane that happens in 2020 or something like that. Is our tool doing that? And really, the answer to that is, again, the GCMs aren't really predicting that. Basically, it's a function of modeling like this. A model will typically dampen the extremes, and I think that the GCMs are doing that. They're cutting off, large tropical storms that occur, and they're cutting off very long droughts that occur. And what we plan to do, like I said, I think that what we'll do is we'll take models that the reinsurance industry uses, because they have a pretty good lock on those kind of storms. Or at least in terms of their occurrence. Landfall is a different question, but in terms of their occurring, they have pretty good lock, and they have a good lock on how big those storms are going to be. We can add that knowledge into our forecast, and
Where do they
therefore,
get their knowledge?
it's just a different kind of modeling that they do. Like the GCM, that is the basis of this, is not the kind of modeling. They're doing more statistical modeling, and they'll do a physical model, but just of the Atlantic Ocean, so it's more focused and captures the physics a little bit better than the GCMs do. So I think that's our next source. We have to add that in. We'll continue to use the GCMs, but we'll add in the extreme analysis as well. Yes, sir.
Following up on David's point, is part of that issue of trying to predict larger storms because the probability is prediction is so low on a kind of a 15-minute time step as compared to a longer time step and a yearly time step, probability of being a big storm is a bit easier on a yearly basis, but the probability of getting a storm at any 15-minute interval is pretty low.
Right, right. You're asking about black swans, I think. That's really the question. The question is the probability of getting a large storm in a 15-minute time step interval, that's pretty low, whereas if you look at it at longer time scales, the probability increases and it's easier to estimate the estimate the occurrence. That's true. It's easier to say, 15 storms will happen this year versus a large storm is going to happen at 9:20 p.m. on August 17th or something like that. That's very, very hard to do. And that relates to the black swan idea. A black swan is basically something that none of us has ever actually seen a black swan, have we? Okay. All right, I'm taking that question back. That's not what I was looking for as an answer. Okay, I have never seen a black swan, and they're typically pretty rare, and so, yeah. And so there's a theory out there that those sort of events are ignored. Those statistical events that are very, very rare, they're ignored by most analysis. Whereas the theory is that they do actually happen more often than you think they do, and when they do, they're devastating. Great Depression is an example, that kind of stuff. And so, okay, I've gone in a big loop here to answer your question, and I've gotten off path here. But I think the answer to your question, therefore, is we're not really trying to estimate every 15 minutes whether it's going to rain with that kind of probability. We're just using this historic library, which, remember, it's a library of storms, so it's not just 15 minutes. A storm could last for 2 days, and we have every measurement over the 2 days. And we are inserting those storms so that we eventually get the 15-minute time steps, but we're not really asking the question within the analysis, is it going to happen in this 15 minutes or that 15 minutes? It's more asked on the daily time scale.
Is it gonna rain on bigger than?
You tell me. Thank you. It's okay.